Hi there, it's Matt Heffernan. Welcome back to my channel. This is the fourth episode in my new vlogging series. Well, it's relatively new now, Slithy Vlogs. And this is an informal look at some of the things I have going on, little one-off demos, things that don't fit in one of my main, really heavily produced and written episodes. And the title of this one, as you can see, is Sectionality. And what we're going to do today is in response to some questions that were coming up within the community in terms of how do you access different parts of memory? How do you access them if they contain code and not data? And how do you actually set up your source code and your build environment in order to do this? So we're going to take a look at that right now. This is kind of jumping ahead. These are some things that I've not covered in my assembly tutorial series, and I'm not sure if I will devote much of an episode to this stuff, but I thought this would be interesting, that we could just take an informal look at some of this and just play around with it and give you sort of the bones of an application, of a framework, if you will, of a multi-sectional application. And so we'll get right into that. Let's see. So first, let's take a look again at our friend, the memory map. What we have is a lot of RAM. Of course, we're very blessed with the X16 to have a relatively enormous amount of RAM for a 6502 based system. We have it's all RAM up through hex 9EFF, but we don't have full use of that necessarily. Of course, we have the 0 page, and as we saw in my last episode of the tutorial series, there's parts of the 0 page that are used by the kernel. If you're using certain subroutines within there, they will make use of that, so you don't have completely unrestricted use of everything on the 0 page. Of course, you have the stack. You don't want to mess with the stack, that page, page 1. And then we have a segment of RAM from 0 to 100 to hex 7FF. And that is a segment of RAM that is used by both the basic interpreter and the kernel. Now, if you are writing an application in assembly language, you don't need the basic interpreter to be running. So you don't need any of that RAM that the basic interpreter uses to just do its business. So all you need to keep is keep your hands off of, that is the part of this segment that the kernel uses, which is only the first hex 200 bytes. So from hex 0400 up through hex 7FF, that's what's called the golden RAM. And it's not a lot of data, but basically once you're into executing a machine language code, once you've done that basic syscall to get out of the basic interpreter and just run straight up machine language, straight to the CPU, no more interpretation, then you have free reign to do whatever you want with that. You may not be able to go back to basic or take advantage of hacking into the basic interpreter and using some basic functionality. You're just going to leave that behind, do everything in assembly, and then when you're done, and maybe you have to reset the unit. No big deal. So, I mean, it's an 8-bit system. That's why we got it, so it's easy to reset. So, but what we normally do is we put our program starting at 0801, and that's the address where the basic interpreter, when you say load and then run without any sort of extra arguments other than the file name of the program for load, that's where it's going to put it. It's going to load what a general program is going to have a header that says load me at hex 0801, and then it will have a syscall in that to start running at hex 080D. And that's where the actual machine language will start, and it will go ahead and run that. And all the examples that you've seen on my channel, that's exactly how they all start, is with that that perfunctory segment header that are at the beginning of my programs. That's what signals to the to CC65 what I intend to do. And this is going to be a straight up program. We're going to start machine code at 080D, and we're going to be able to load it and run it using all the default behavior of the basic interpreter. Well, of course, you don't have to do that. Obviously, it makes sense that you want to place your program within the largest part of unspoken for user space RAM, but you might want to take advantage of other things. First of all, that golden RAM, it doesn't go anywhere. If you're in the machine language program, nothing else is going to use it. It's just sitting there doing nothing. And it's always there. It's not banked at all. So you can put stuff in there for easy access, and you'll have it for the length of the execution of your program. Of course, also, we have banked RAM, which isn't, quote unquote, always there, but there's a lot of it. And we have these 8 kilobyte windows. The base model of the X16, the one that's going to be available at launch, pre-assembled, will have 64 banks of RAM, which is 512K. Now, the first bank 0, is used by the kernel, and we can't really use all of that. But from bank 1 on, it's total user space. Do whatever you want with it. But of course, you only have those 8K windows to deal with, and so you have to switch your banks when you go back and forth them. But that doesn't mean you can't put code there, right? You could have, if your code is so big it doesn't fit within that 37.75 kilobytes in the main basic program part of RAM, well, you're going to want to take up a bit of that other stuff. You're going to want to take up that almost a kilobyte of kernel of the basic RAM, the golden RAM. You may take up 8K here or 8K there of these RAM banks to just get a little more code. And so we're going to take a look at exactly how you would do that, and even more specifically, how you would set up CC65 to allow you to do that. Now, of course, we can't just load something across golden RAM and the basic program RAM and a bunch of RAM banks all in one load. It doesn't work that way. You can't load stuff, say, to the I/O space. So we can't bridge that area. That can cause bad things to happen. We don't want that. So to prevent bad things from happening, we need to load things in piecemeal. So our initial load will be here, this blue box, which is what all of our programs have been so far, is the main part of the program. It's going to be loaded at hex 0801. It's going to have the basic header with the syscall to start the machine language program at hex 080D. And that's where we will specify the origination point of our main program assembly file. And that, in that program, it will go and load a program that is been built and configured to be loaded into golden RAM starting at hex 0400, and we'll have fixed entry points into that, actual subroutines that it can call. And then it will have, in this particular example, 2 more programs that will run that were configured for RAM banks. One for RAM Bank 1 and another for RAM Bank 2, both starting at the beginning of that RAM Bank window at hex 1000. And that's what we have to be able to do, is build essentially 4 different programs that are each have their own configuration, although the RAM banks is basically the same configuration, just a matter of where we load them. But still, they each have their own specific configuration, their own way of structuring themselves, and that the product that we get out of it, the actual artifact that we're going to be loading in, both from the basic interpreter and from this blue box main program, are all set to be able to be loaded with minimal intervention. So let's take a look right now at what that means. So first, here's our main program. We've got that standard preamble right up here. Maybe I should probably do the highlight line with the selection borders. So, because this time we're not just going to breeze past this, we're going to talk about this actually a bit more. So we can see here that the first line, we are setting the origination point at 080D, even though our artifact will have a header saying load me at hex 0801. And that is because of a lot of the window dressing we have on here, and the fact that we're going to be building it with the default X16 configuration. And CC65 will assume by default that you are trying to load something at that address, and you're going to need the header with the tokenized basic syscall to whatever your origination point is, which in this case is 080D. So we need these three segments that are totally perfunctory. We could have a custom configuration that no longer requires those, but for this case, we're just going to take the path of least resistance. We're going to put those in there, and then the main one we really are concerned with is the code segment, and that's where actually everything in this assembly program is going to go into. It's going to go into the code segment. So first, what we do is we include a couple of files. Now, neither of these files have code in them. They are include files, just like header files in C. So they don't instantiate any sort of memory storage. They don't define any programs other than perhaps macros. So when we know that when we get here to jump start, that's actually going to happen at hex 080D. That these two includes up here are not going to take up any space. So if you've seen some of my other videos, you might have seen this X16.inc. I haven't introduced it yet in the assembly tutorial series. I've been always taking parts of this out and sort of copying and pasting it into the different programs. But here's how it is. So we can see some familiar things. We've got the default device number, the SD device. Oh, I never put that in here. I probably should have done this. So I could say here, SD device. And that would be the device number that I use. And then I have those kernel registers for the ABI, the 16-bit ABI. And this is all of them. I got all of them in this file. And then I have this sort of 0-page user space area, just some things that you're going to want. You're going to want sort of these scratch pointers. And so I just defined 4 of them in there for convenience. So every program I do, I don't have to go about and say, all right, well, I guess I need ZP pointer 1, 2, 3, and 4. And you'll notice here specifically with pointer 1, earlier versions of this file placed this at 0. And in fact, pointers 2, 3, and 4 were at 2, 4, and 6. And of course, those don't work because event 2, 4, and 6 got taken up by the ABI, and now 0 is going to be taken up by the RAM and ROM bank registers. So this makes it a bit more forward compatible by saying, all right, you'll go ahead and just use 7E for ZP pointer 1 if you need to use that. And then I've got all of the IO registers, and then our ROM banks. Of course, this is still targeting R38, so it has the old R9F60 and 61 for the ROM and RAM bank registers. It's not set up to be 0 and 1 like it's going to be on the actual hardware. And again, this is for compatibility. So when you write something using this, it's going to work on the release version of the emulator, including the Commander X16.com web-based emulator. So then we have these other things. We've got the YM2151 interface. We've got the special GIF control, so you can create animated GIFs from what you do in the emulator. I'm sorry if I say GIF offends you. It's pronounced GIF. All right. The folks at CompuServe called it GIF. I call it GIF. It's called GIF. Oh, hashtag controversy, right? So then I have here all the different ROM banks. Of course, generally we only have it at the kernel or the basic, but if we did need to access others, that's already defined there. These are going to come into this program. We have the RamWin banked addresses here. So the RAM window starts at hex 8000, and each RAM window is 2000 hex in size. And of course we got the ROMWin, but we're not going to see that now. Then we have all of the kernel subroutines, and the one that we are going to use for the first time in any of my videos is this one, the JSR FAR. Now you notice I specify it a little further. I call it the JSR FAR kernel address. And that's because what I'm going to define JSR FAR to be is a macro, and we're going to see that in a bit. Now, first let's get through the rest. We got a lot of kernel subroutines here. All right. And then we've got a couple of vectors here. There's Hispanic and init, things that you can write to or rather read from to get some status information. These are, of course, vectors into ROM. They have generally pointers and RAM that you can check out. And of course here, these are the fixed VRAM addresses. When you are first starting up the X16, the ROM is going to place the PETSCII characters at F800. And then you have the fixed segments of VRAM for the PSG, the programmable sound generator, the palette, and the sprite attributes. The sprite video is coming soon. Don't worry if that's what you're waiting for. That's going to be sort of the big finish of the tutorial series. And then, of course, these RAM vectors, we've been playing a lot in my videos with the IRQ RAM vector. There are, of course, also RAM vectors for break interrupts, for NMIs, and even this guy. We won't get into what this is. All right. Another helpful macro I have in this file. Again, this file, versions of this are in most of my projects. This is based on the one that I have in the XCI repository, and I sort of keep that version up to date for all my other projects. And if I refer to somebody to it, it's like, hey, you want the general purpose X16 include file? It's right here. Just get the latest from the XCI repo. So here I have this macro, Vera set address. So you can just put in a address and a stride value, and it works pretty well. Of course, what it's going to do is I don't even know. Does this even work anymore? I haven't played with this a whole lot. So if a stride is less than 0, yeah, it's going to do this whole weird thing. Basically, I think this only really works for the power of 2 strides. It doesn't work for the bitmap specific strides. So it's not all purpose. A lot of the time you don't even want to use this. You have other programmatic needs where you want to be able to set those banks, the bank and the high and low parts of the address in a more specific fashion, in a programmatic fashion, not just passing it a 17-bit address like you can with this macro. But a macro that you would want to use anytime you want to use JSR FAR is this one, is the JSR FAR macro. And the way JSR FAR works is you do a regular JSR to it, do JSR to the JSR FAR address in the kernel. And what it expects, the kernel does some nasty little business with the stack and says, all right, well, what's the return address? And the return address would point to here. And it's like, well, that's where I am going to get the actual address I'm going to execute. And then after that, I'm going to get the bank that I need to switch to before executing the subroutine there. And then when that subroutine returns, we're going to give it a return address. We're going to suck this stuff that was on the stack off and push back an address to get right past this byte where the bank is stored, so that then what we can do is just call this macro, give it this far address for a RAM bank between 8,000 and BFFF hex, and then a bank from 1 to 63. And there you go. We're executing code that we have loaded into one of the RAM banks. And then the program will return right after the next instruction after that macro call. Nice and easy. So we'll see that in action here, back here in this program. So anyway, that's what X16 Inc. does. It gives us all that stuff. Of course, none of that took up any space. It was just some constants and macros. Then we have print Inc. And print Inc. is just another define, defining the Petsky return character. And then a macro called print line. And this works exactly like every print line you've ever seen in every other program. It will print a string and then follow it with a new line sequence. And the new line sequence for the X16 basic is just a return control character. So what we can pass this macro is the address of a null terminated string, and then we will just print it out. And that's what it does. It will initialize X to 0. You'll notice here we've got a colon. We have an unlabeled label, effectively a nameless label, where we load a byte off of that 0 terminated string. If we have hit that 0, that null termination, we will branch ahead to the next colon here with the next label, and that is this unnamed label that will simply load a return into A, that return control character, and print that out. And so that'll be the end. But until that happens, everything that it loads from the string, each non-null character, it will have that in the accumulator. It'll call char out, and it will print that character out to the screen, and it will increment X so that we can keep going. Of course, this won't work with any strings that are 256 characters or more. That will cause it to break down. But that's okay. Of course, it would be an infinite loop if you went more than 255 characters, or rather, 256 characters, I guess, without a null termination. It would go in an infinite loop. But we're dealing with print line here, and at most we've got an 80 column display. So let's take it easy. Let's not try to hurt ourselves and just pass a string that is 80 characters or less, and everything should be fine. So that's all this does. It doesn't do any space, just defines a macro. And then here we do our jump start, and we're still at hex 080D. And then we have some data, because before we get to start, we need to just define a few things. So we want a null terminated string that we're going to print out called main, and it's just going to print out main program. Of course, it'll be printing out in all caps because those are unshifted characters within X16, so we just do them as lowercase within the source file. Of course, also, we have this golden start. This is where golden RAM starts, so we need that later. We're going to assume that this program, golden.prg, is going to be loaded at the golden start address, and that bank1.prg and bank2.prg will both be loaded into the beginning of their respective banks' RAM windows. And then we have a little label here to say, all right, this is where bank2 FN stops. So what we do is we start by doing an LFS. And of course, we want the 1 for the logical number because it just has to be something. In this case, we use 8 or SD device. Now that I'm using this include file, I can just put in SD device instead of hard coding #8. And then the Y, the secondary address, I'm not going to put 0 in because everything we're loading is going to be properly formatted to have its destination address. And in fact, they would break if they were not put at their destination address. So we're not going to mess with that. We're going to make sure that these programs get loaded where they're intended so that they don't fail. That's on the folks that are creating these programs. Those folks are me. That's all me. So it's my responsibility to make sure that my secondary programs are built correctly and have the correct header in there. So you tell me where you need to be loaded, and I won't get in the way. So that's what setLFS does. It gets that secondary address ready. And then here we call our first call to set name. We'll bring in the bank one. Uses bank one file name as the end of golden file name, so we get the difference there to get the length of the golden file name. And then we put in the address in X and Y for golden file name and call set name. And then we call load with a 1 in the accumulator. And we don't care what's in X and Y because remember, back up here, we set our secondary address to 1 and to something non-zero. And that means that when this load happens, that whatever those first 2 bytes in golden.prg are going to be assumed to be a valid address header, and that's the address we're going to load it. And we are assuming that that will be at golden start, or that at least, golden start will be the address where there is a subroutine that we can run and will return back to us safely. So going further, we load up the bank programs. So we load up the bank1 file name using the bank2 file name as the end of that one to compute the length. And again, we're loading 1 into accumulator. We know this is bank 1. We also need to store that 1 in the RAM bank so that we are not in RAM bank 0 as we are by default. And then we load that into RAM bank 1. And also by having 1 in A. And again, don't need X and Y set to the address. The bank 1 file name is going to put something of use starting at hex A000 because we're depending on it. That's the actual address we're going to be calling later. So it better put something good there. And then the same thing goes with bank 2 file name. And we're going to use that end file names label to compute the length of that because we just know that bank 2 file name is the last one. And then we load up the RAM bank with 2 because this is going to go in RAM bank 2. So we need to set that. And then we need to revert A back to 1 and do the load. And so that the bank 2 file name, bank2.prg, will get loaded into that RAM bank 2 that we just set. And then we are done loading up all of our data, all of our programs, rather. We're not loading data, we're loading programs, although those programs do have data inside them that we're expecting to see. And then we do our 1 bit of our local data in the main part of RAM by doing println main. So we're calling our println macro. We're passing main to it. If you remember, main is a null terminated string. So we should expect main program and then a new line to happen when we do this print line. And then we do a JSR to golden start. And of course, this assumes that this, when we loaded golden.prg, that it has a subroutine starting at hex 0400 with valid code that will return to us. And then we do our JSR FARs. And again, we are assuming that when we loaded the bank1 file, the bank1 program, that it has a subroutine starting at the A1000. Same thing with bank2, that there's a subroutine starting at A1000 in bank2. And in both of those cases, they will come back to us. And then after that, we'll just return to basic and we're all done. So what does it look like to build this? Now, this one's going to be just like every other one we did. We are doing -T CX16. So we're doing a Commander X16 build, and we're going to output segments.prg. We're going to get a listing to just check, make sure things are okay, and we're going to pass in the assembly language file. And that will get us, as we expect, that header to do the syscall in BASIC to get us into machine language land. But then we see here the commands that we use to build the other three programs. And you'll notice they have this special little argument in there, the -C. Not to be confused with the -c, which is used for build. You wouldn't use it with CL65. You would use it with CA or CC65 to build loadable object files. Or linkable object files, sorry. But here, this is specifying a custom configuration. We're not going to use the standard Commander X16 configuration in CC65. We need to define our own so that our program file will be formatted correctly. So first, let's take a look at the source code. Right off the bat, you'll notice there's a different org value. Just like we were expecting in that main file, we are originating it at the beginning of Golden RAM at hex 400. And then we only needed one segment. Well, how about that? Well, that's because we are in complete control now of this configuration. We don't need to list a whole bunch of others. All we need to do is say, yes, this is where code is going to be. Because everything has to be in a segment. You can't just define stuff to exist in CC65. You have to be in a segment. So we're going to have our jump start here. Now you notice, even though this is going to occupy RAM at the same time, that all those names, all the labels that existed in that main program, those don't apply. Those have all been assembled out and just turned into stupid number addresses. They are no longer linkable, referable, nothing. They aren't there anymore. So we can just go ahead and have another label that says start. It's not going to conflict. This start will be at hex 400. We include that same print.inc, so we get our print line macro. And then we have our 1 bit of data here, which is a null terminated string that says Golden RAM. And the start of this program is going to print that. And then it will return. And that's it. It's not a whole lot. We didn't really need to take up Golden RAM to do this. This is just, of course, this is an illustration. But this return will take us back to the main RAM from when we called Golden Start, which is 400. So we have to do a bit of hard coding here, sort of. Say, all right, Golden Start's at 400. And over here in Golden ASM, we're saying, all right, we're jump start, and we're going to a place where it's all going to be code starting at 400. So yeah, we've got that underway. Of course, you could always create jump tables. That's an easy enough thing to do, is to have a bunch of jump commands that were in there and be able to better control what those different addresses are, and that's basically how the kernel works. And you could do the same thing within a segment of RAM that's outside that main segment, like the Golden RAM or in the banked RAM. You can do all that. So that return will get us back to after we do JSR Golden Start, and we'll move on to there. So that's it for Golden ASM. But of course, we look back here, we are building it with this minus capital C, saying, all right, the configuration I want to use is that X16 golden.cfg. So let's take a look at that. What does an actual CC65 configuration do? I haven't really shown that in any of my videos outside of my Atari 2600. Go back, of course, if you're not a subscriber, my goodness, at this point, please go back, subscribe to my channel, and take a look at all the cool stuff I got going on there. I have my assembly tutorial series, I have these vlogs, and I have a bunch of demos, including stuff I've been doing for systems besides the Commander X16, like the Atari 2600. And in order to do that, I had to create my own custom configuration in order to do ROM banking within the 2600 to use a banked ROM, which is period appropriate, but folks are using other assemblers. They're not using CA65 generally. So I had to be a bit of a trailblazer in that respect. Anyway, so now for Commander X16, we also have to sort of blaze our own trail. It's like, well, what does a program in Golden RAM, what sort of configuration does it need? And generally, we're going to expect that a program in Golden RAM is going to be more or less limited to that Golden RAM, that it's not going to expand into the main part of RAM. It's going to be more or less self-contained. So what we need is our feature, our start address is going to be at hex 400. And then we need to have a load address, because we want to get that header in there. We want to have our header say, yep, this is where it's going to be. And here we say, all right, within memory, at the very beginning, we are going to say, all right, we are not really at the start address at this point. We are sort of two behind the start address. So we're not really going to start loading data into memory until the third byte. So those first 2 bytes will be that load address, and it will be a 2-byte affair. We don't need these leading zeros here, but basically, yeah, it's 2 bytes. This is just copied from another one from the default configuration. And then I need to create a memory segment, or rather a memory load point called golden. And this will say, yes, we need to have this defined in our program that will make this required. And it will start right at the start. So golden will be the start of the program. And we have 400K, or not 400K, 400 hex of data that we can put there before we bump up at 800. Technically, I guess we got 401, but, you know, we'll just keep it at 400. So now we can actually define our segments, and we have the necessary read-only segment of the load address, which is not actually going to get loaded, but it's going to be there as part of this program file. And then the actual code itself, which is going to be at the start of Golden, and that's going to be all RAM. That's read-writable, so we can expect not just instructions to go there, but also RAM variables can go there. Everything will be totally cool. So that will do that. So let's take a quick look right now. Let's run that build, and we'll take a look at some of the files we have here. Now, if we look at our just the segments.prg, we'll see here the header we're expecting. That, of course, is little endian. So 0801 is the address, and then eventually we get up to over here. If we look at segments.list that we generate, and get down to, yeah, see, it's all 08OD. So at 08OD, we expect to see the 4C3908 for that jump start. And there we see it, 4C3908. There's that initial jump start, and then our data. where we can see here that corresponds to all those strings that we have in RAM, and those are now uppercase ASCII characters at this point. And so yeah, we've got all of this tokenized basic over here. That's what all of this is tokenized basic. So so that's in there as we're expected. So that should be able to be just automatically loaded and run just like all the programs we've had before. But now let's take a look at golden.prg. Big difference here. First of all, we have a different header here at 400 hex. Of course, little endian. So 04, then 00. And then we go right into the code. The same thing. We have a jump start. So we have that unconditional jump here, the 4C opcode, and then 040E. And that's the actual start of our executable code. If we look at, where is it there, golden.list, and we'll see that's what it comes out to, 040E, because we have all of this data. Once we get past these includes, here we've got the data for our string, and then 40E, hey, that's where our program starts. That's our start. So mission accomplished there with the golden RAM. So then the banks should be pretty easy. It's also straightforward. If we go back to our build script, we'll see here, these both use the same configuration file, rambank.cfg, because from their own perspective, it's the same. They're going to be loaded into a bank RAM. The RAM banks don't know which bank they're in. That doesn't figure into their code. They only have 16-bit addressing within the from the perspective of the code itself. So let's take a look at that real quick. Now, very similar to how the golden program was, we have a .org, this time at 1000 hex. So this is going to be at the RAM window, the beginning of the RAM window. And we're going to say this is our code segment. We're going to have a jump start. We're going to include that print line macro. And then we're going to have our string, our zero terminated string. That's going to say rambank1. So we better be loading this program into bank 1, otherwise it's lying. But again, he has no idea. So he's going to call that macro and then return. Now bank 2 is the same. And we can see here, and we can guess that these are going to be the same addresses. This bank 2 and bank 1, those are going to be at the same addresses. The only differentiation will be the current RAM bank. And we're just going to have to make sure we handle that. And in each case, we have a return. And that return is going to return from a JSR far. And that should get us 3 bytes past wherever JSR far was called, which our little macro down here will take care of. So it'll make sure that after the JSR far kernel subroutine is returned from, that it will jump over both the address and the bank number, that it will the kernel will use introspection to switch the correct bank, and then run this program so that that far address should be that A1000, which will execute the jump start in both of these cases. So now let's take a look at its configuration. It's very similar to Golden. If you remember here, you can see it doesn't do a whole lot different. The big difference is going to be the address. The start address, instead of 4000, it's 8000. And then what we're going to have is did I not get the I think I might not have. Oh, I didn't pull that in yet, did I? There we go. So on another machine, I had fixed this up a bit. So here now we have a new memory load point called rambank, and it will begin at the start address, which is 8000. And now its size, unlike here, we had the Golden load point. We can only load up to 400 hex data. we can load 2000 hex data. A full 8K can be loaded at that RAM bank. And then that's it for the memory, and we'll have the same sort of thing where we have our load address. We need to have that 2-byte header, and then our code is going to use the RAM bank memory load point to start loading stuff into. And that's it. So now if we take a look, let me build again. We'll make sure we got everything built with what we did. And now we do an XXD on, let's say, bank1.prg. And we can see there, it's got the load point is at 8,000 hex, little endian. And then we can see here the same jump instruction, and A0OE is the address. So it's again going to be RAM bank 1 takes up the same number of bytes as golden RAM, so it is going to be 14 bytes past the beginning is where everything's going to start. And you can see here, so this data up here is different because it has a different string, but we've got the 0 there. That's the null termination of the string. And then we have the code, which is more or less identical of everything we're doing, except you can see here we have an address of instead of 4003 or 403, we have 8003 as the address of the beginning of the string in memory. And that's it. So now everything should just work together. So we go into our emulator. We're going to make this big. And then let's do a screen 0 so we get bigger text. And we'll load segments. Oops. I always want to do the shift. Segments.prg. And run. And there it is. It just went right through. It printed out the main program. It jumped into golden RAM, printed out golden RAM. Did a JSR into RAM bank 1, and then a JSR into RAM bank 2, and everything printed out. All of that data and code from all 4 different segments all came through, and we're good. Right? Oh, let me check something right here. Did I put in the I don't have the Patreon thing in here, so because we're here, we're at the end. So let me go ahead and close this out, and let me go back to my little sandbox area where the magic really happens. And so if you haven't subscribed yet to the channel, please do that, and you can see all of the awesome stuff I have on there. You can look at the description in this video and get all the materials for this. You can get that repo and see everything I did, and go ahead and freely reuse that for your own purposes. And of course, also subscribe to the channel. Click that bell for notifications so you know when the next episode comes out. I'll have another vlog next week, and in between, I'll have a more polished and edited video that you may enjoy more if some of this was a little too loose and shaggy for your liking. But in any case, if you want to see these episodes before they come out, you can join up on Patreon, pledge as little as $1 a month, and get access to these videos as soon as they're complete, and you won't have to wait, just like these fine folks did. And they're the folks that really make my channel run, and I can't thank them enough. So come and join us. We got a lot of exclusive content out on there. But otherwise, please just subscribe and like this video and comment, and let me know if there's something else that you've been wondering. How do I do that? What does that look like? What can I really do with the Commander X16? Or how can I use some of this knowledge to apply to other systems? I'm up for anything on these vlogs. So hit me up, and I'll talk to you later. Bye-bye.